Believe it or not, the first modern robot was a weapon, the torpedo. Delivered by its inventor Robert Whitehead to the Austrian military in 1866, the Whitehead torpedo was a self-propelled underwater bomb that could maintain its depth using a mechanical pressure sensor. Even before Whitehead, back in the 19th century, Sir George Cayley, an engineer, had examined the curved wings of birds and tapered shapes of dolphins and trout, and seen in them the designs animals had in nature in order to minimize mechanical resistance. While Cayley invented the first glider to carry a human aloft in the 19th century, having correctly identified the aerodynamic forces of lift, drag, weight, and thrust, we also know today that when we see a torpedo-shaped body in a robot, it is built that way on purpose, on purpose, for streamlining. Torpedo-shaped bodies are built to go fast and straight, and by the turn of the 20th century, the torpedo's inventor Whitehead had added a gyroscope to stabilize his mechanical beast's headings. Motions guided by sensors are at the heart of autonomous robotics, and the success of the fully autonomous robot known as a torpedo has led to its widespread and lasting use. To this day, military robots lead the pack in terms of innovations in robotics. As both Cayley and Whitehead glimpsed, years ahead of their time, military robots have to be customized to operate in the air, on and under the sea, and even in space. That's partly because robots designed for war must operate in a staggering array of workplaces and carry out a multitude of tasks. A very brief list of robotic missions in the 21st century military would include the following: hazards investigation, route clearing, mine detection, vehicle inspections, explosive ordnance and bomb disposal, emergency response, carrying supplies and people, patrol, search and rescue, communications and electronic warfare, and defensive and offensive ops. But military robots have to be customized for another reason too. Now, let's recall science fiction author Isaac Asimov's famous 3 laws of robotics. They appeared in his 1950 book of short stories, I, Robot. In one of those stories, Runaround, Asimov lays out his principles summarized here. First, robots may not injure humans. 2, robots must obey humans except if doing so would harm a human. And 3, robots must protect themselves so long as they obey humans and avoid injuring them. But from Whitehead's torpedo onward, many military robots have been what we would refer to today as self-guided weapons. They were designed to kill and destroy. Weapons such as torpedoes and aerial bombs appear designed to violate all of Asimov's laws. So how do we exercise safety and control over these robots? In this lecture, we'll examine some of the tensions between semi-autonomous military robots and our need to oversee their safety and control. There are trade-offs to consider between the speed of action and the complexity of the plan, and the identification of friend or foe becomes far more important in military situations than in any other area of robotics. One way to maintain control, to make the robot obey you, is to maintain communications with it and give it limited autonomy to act on its own. Flying for the U.S. Air Force, the MQ-9 Reaper, an unmanned aerial vehicle produced by General Atomics, is controlled by trained pilots on the ground. Air Force pilots and their human commanders make the decision about when the Reaper can fire and what the target will be. While partial autonomy keeps control in the hands of the humans, it presents a security problem. Radio communications can be hacked. So one robotic solution to the changing situations like being hacked is called adjustable autonomy. For example, if a radio link is cut, many drones automatically fly themselves home. They monitor communications and then adjust to the change in situation and become fully autonomous. A second concern about maintaining safety and control resides in how decisions are made. In robotics, we have 2 main kinds of decision-making systems: behavior-based control and model-based control. Behavior-based controllers are fast, reflexive systems like the escape response on a Roomba vacuum cleaner. What triggers a response is a sensor. When it detects an object or a change in environmental conditions, that information triggers the program software controller to send instructions to the motors of the wheels to initiate a series of movements that we call an escape. If multiple sensors are triggered, the controller allows one reflex to overrule the others, a decision that makes it makes based on a set of priorities that are programmed in its code by humans. Model-based systems are relatively slow, deliberative systems that can weigh information from multiple sensors, calculate high-level inferences, update maps, and make plans for actions in the short and long term. And at the heart of this kind of controller is a model of the world that includes the current state of the world and the robot as part of that world. As both change, the model has to be updated in order to remain accurate and useful. With a model-based system, decisions are made based on the current state of the robot and the desired future states of the robot that are required in order to achieve the explicit goals programmed into it by the humans. The tension between these two systems can be characterized as a trade-off between speed of action and complexity of plan, speed versus complexity. In military situations, we often need both. Sometimes a soldier has no choice but to decide reflexively, fast, and that's where his training comes into play. An officer, removed from the front lines, can take time to gather information and slowly create multiple plans before deciding which plan is likely to lead to the best chance of achieving the desired goals. Many robots combine fast and slow autonomous control architectures. Even so, both types of control architectures rely on the quality and accuracy of the information provided by sensors and by the models of the world. But nothing is ever certain, and the field of probabilistic robotics recognizes that explicitly. Probabilistic robotics grapples with uncertainty in mathematical terms, building and updating models of the world, and the robot that create robust behavioral choices in the face of that uncertainty. The autonomous robot makes decisions based on what it knows and what it doesn't know, and its degree of uncertainty about both. Probabilistic robotics have helped build the very successful and safe autonomous robots we know as self-driving or driverless cars. Google driverless cars have logged almost 1 million miles on the roadways in California without having been the cause of a single accident, although one driverless car was hit by a car driven by a human. Compare that to the average accident rate for human-piloted motor vehicles in the US, including fender benders, and any incident you might report to your insurance company. 3.7 accidents per 1 million miles traveled. Robots may be much safer drivers. The point here is not only that we can make autonomous robots operate safely in dynamic real-world situations, but we can, with sufficient investment, make them operate much more safely than humans working under similar conditions. Can we do the same in war? In warfare, the equivalent of the rules of the road are international treaties, such as the Geneva Conventions. Protocol 1 is an amendment from 1977 outlawing, among other things, attacks on places of worship. This rule could be written into the programming of an unmanned aerial vehicle. Any place of worship is indicated on the robot's model of the world, its map, as an off-limits area. Even with this programming and a probabilistic controller that accounts for uncertainty, we could never ever expect a robot to operate perfectly. And here's why. The robot could accidentally bomb a place of worship if the information in its world model was inaccurate. Imagine that a community creates a new or temporary place for worship during the armed conflict and it keeps it secret, or the map makers never identified the space correctly in the first place. We would also consider it an accident if a missile fired by the robot intended for another target malfunctioned for reasons that had nothing to do with the programming of the robot and hit the place of worship. Also, there's nothing to keep an unauthorized human from reprogramming the unmanned aerial vehicle. But there's one thing we wouldn't have to worry about anytime soon: a robot with emergent self-consciousness, free will, and a sudden desire to kill humans. No one working in robotics, artificial intelligence, psychology, or neuroscience has ever created a computer program or a machine that is conscious and self-aware in the way that most humans think of those experiences. Could it be done in the future? Yes. Given that we're still trying to model and understand the brains, bodies, and behaviors of much simpler organisms such as worms, however, we're a long ways off from creating robots with human-style consciousness. That remains the stuff of science fiction. The science fact is that while we can build robots with behavioral autonomy, their autonomy is not of the same type that we humans possess. And that difference in how robots and humans work is a great thing, practically speaking. That's why robots are better drivers than humans. They don't get tired or distracted or emotional. And that's why, if programmed correctly, robots can be better soldiers. But we have a long way to go. One area in which robots are not yet capable of being better soldiers than humans is in the identification of friend or foe in non-traditional battle situations. Now, to be fair, this is a huge problem for humans. An occupying army faces this problem continuously. Is that pedestrian on the streets of this city a friend or a foe? The general problem is called combat identification, and the military has been working on a technological solution since World War II with transponders that were coded for signals on vehicles or individuals that can be used to identify positively a friend, as can careful tracking from known starting positions. But confusion exists if a transponder is broken or tracking is interrupted. In addition, the activation of a transponder can also alert the foe to the presence of your own soldiers. So the difficulty of automating combat identification and general concerns about maintaining safety and control are two of the reasons that the most widely deployed military robot, the Predator unmanned aerial vehicle and its descendants, is operated by a human pilot and given only partial autonomy. The original Predator unmanned aerial vehicle was of modest dimensions, sporting a fuselage length of 27 feet and a wingspan of 48 feet. It's an old-fashioned, propeller-driven plane. The Predator was first flown in 1994 and entered production in 1997. The Predator and its weaponized descendants, the Reaper and the Avenger, have served the U.S. Air Force, U.S. Navy, U.S. government, and a host of other countries. Predators are technically considered to be part of an unmanned aerial system because they are remotely operated with humans in the control loop. The robot does all of the autopilot work, navigation, flight control. The humans exercise high-level control of goals and decision-making. Here you can see two members of the U.S. Air Force closing the control loop in a Predator unmanned aerial system. The year is 2007. The place, Iraq. The Predator has just taken off and they are performing a series of in-flight equipment checks. Captain Cole on the left is the pilot. Airman Oilo on the right is the operator of the Predator's sensors. Their job is to work with the Predator while it's within a 25-mile radius of the base so they can recall it if they detect any problems. If the Predator checks out, then they'll do something that at first blush seems crazy. If it checks out, they'll hand over the control to a different set of Air Force operators who are sitting in Nevada. So two things make this handoff possible. First, communications to and from the Predator are handled indirectly via satellite. Unlike regular radio control operations, control via satellite allows communications over the horizon, out of the line of sight. Second, navigation anywhere in the air is made possible by the Global Positioning System, which we know as GPS. GPS was created by the U.S. military for aerial, water surface, and ground vehicles, both manned and unmanned. In robotics, navigation is one of the most fundamental problems that any mobile robot has to solve. You have to know where you are and in order to get where you want to go. GPS works as a system of navigational beacons that can be used to calculate your position. The current GPS system is a network of 29 Earth-orbiting satellites. The robot needs the ranges and locations of 4 of those satellites to calculate its position using a process called trilateration. Trilateration involves the simple geometry of overlapping circles in the two-dimensional case, or the slightly more complicated geometry of intersecting spheres in the three-dimensional case. What makes accurate navigation particularly important to unmanned military robots like the Predator is that they can remain on remote station for over 24 hours. If the unmanned aerial vehicle were trying to navigate by dead reckoning, errors in estimating position would increase with time and distance. Navigation does not present a problem for other types of military robots as long as they operate in sight, performing jobs in close proximity to the soldier in front of them. PackBot, created by and produced by iRobot, is a class of small, mobile, remote-controlled robots with partial autonomy that have been customized for a variety of different tasks in close proximity to the operator. They are built to dispose of bombs, improvised explosives, provide situational awareness to first responders, aid search and rescue, collect video and air samples and hazard responses, and detect and localize snipers. In each of these tasks, PackBot increases the standoff distance between a human soldier and the potential threat. As a stand-in for the soldier, PackBot allows operators to have virtual presence and virtual agency. Virtual presence is made possible primarily by the cameras and microphone that PackBot can carry. It can also be outfitted with other sensors depending on its particular task. Virtual agency is made possible by the ability of the soldier to control the movements of PackBot using a video game-style controller. Virtual presence lets the operator perceive the world from the robot's point of view. Virtual agency lets the operator act in the world as the robot. One fundamental principle of robotics is that perception and action depend on each other. Is that object a brick or a case that might contain a bomb? Move closer. Maneuver the arm holding a camera to the side. These are actions that create new perceptions. Is the path clear, straight ahead for movement? This is a perception that is necessary for the desired action. To get PackBot working for you in the field, it has to be deployed first. Man-portable and weighing only 24 pounds without the battery, PackBot can be carried easily by a human and then deployed in 2 minutes. It can be operated up to a range of 1,000 feet via two-way digital radio communications. So a challenge of battlefield situations is terrestrial locomotion. Rubble, uneven terrain, water, mud, and tight spaces often bar access to wheeled vehicles. Wheels that fall into cracks or get stuck in loose sediments can permit the chassis to get hung up and stop the robot dead in its tracks. To avoid that problem, PackBot uses tank tracks. Because the chassis of PackBot is relatively small, just 7 inches in height, tracks alone would not permit it to move upstairs. Yet it climbs stairs easily thanks to an innovative set of actuators called flippers. These flippers, which have motorized tracks, are mounted collinearly with the axles of the frontmost wheels. Operated separately from the chassis' main track actuation system, the 8-inch flippers can be rotated 360 degrees, adjusted into positions that allow the flipper to serve as a motorized ramp, or rotated to help lever PackBot over obstacles. The flippers can also be used to prop up the front of the robot to increase its height for reaching and inspection. As a highly maneuverable mobile robot, PackBot can take tools and sensors into dangerous situations. To carry sensors and end effectors, PackBot can be installed with a manipulator, an arm with 8 independent degrees of freedom. If you use PackBot to inspect a building for threats, 2 problems can undermine your mission. First, you may lose the ability to navigate effectively because you're disoriented in the remote frame of reference of the robot. Second, you may lose communications because of electrical noise, distance, or obstruction. Both of these problems tend to arise when PackBot is no longer in your sight. Here's where the partial autonomy of PackBot becomes very important. In any navigational task, being able to hold a heading is paramount, allowing you to make progress towards a waypoint. PackBot allows the operator to select a heading, and then PackBot will hold that heading for you, even as it moves over uneven terrain. So this allows the operator, who's looking through cameras that experience all the bumps and jostling, to be certain of the robot's course. Heading hold is made possible indoors by the use of a compass and an algorithm based on negative feedback control. The difference between the selected heading and the actual heading in negative feedback control is constantly calculated by the software controller. That difference is called the error, and the goal of the controller is to adjust the heading to minimize the error, ideally maintaining the desired heading without error. But what happens when the communication link is lost? Is PackBot lost too? Not necessarily. PackBot first initiates retro-traverse, which is a fancy name for retracing your steps, or tracks in this case. Because the chassis contains a compass, GPS, and an accelerometer, it can keep track of how far it has gone on any series of headings. Then it can backtrack until the communications link is reestablished. Once recovered, PackBot can be quickly packed up and transported. In addition to the 24 pounds of the robot itself, There's the operator control unit, another 15 pounds that includes the hand controller, radio module antenna, and wall charger. Add a 3-link manipulator arm to your kit, that's another 20 pounds for a total of over 60 pounds with the batteries. While loads of this amount are standard for foot soldiers to bear on their backs, these loads reduce the speed and increase the fatigue of soldiers. Particularly challenging is terrain, like mountains or swamps, where wheeled transports can't go. Here is where a different kind of military robot is being built to literally lighten the load. The Legged Squad Support System, LS3, is basically a robotic pack horse. Built in conjunction with DARPA by Boston Dynamics, which was purchased by Google, LS3 is the size of a horse. This 4-legged robot can carry 400 pounds and, most importantly, can do so over rough terrain. Because the design of LS3 is inspired by animals, we talk about it having a biomorphic body plan. If we had LS3 helping us at home to carry firewood, groceries, or dirty dishes, we'd call it a personal service robot, right? The concept of a service robot conveys the idea that LS3 works in and around its operators, helps with designated tasks, doesn't bear weapons, and is not intended to operate autonomously. Now, what sets LS3 apart from personal service robots intended for the home is that it is large, loud, bearing a gas engine, and extremely robust in the face of challenging outdoor environments and perturbations like weather and loss of balance. These are the kinds of features we have in mind when we talk about a robot being hardened for military use. LS3 is partially autonomous in addition to being hardened for military use. It responds to basic voice commands such as engine on and stop. When commanded to follow tight, LS3 will kick into autonomous mode and follow the human in front of it. What's really impressive about LS3 are its actuators for movements, its legs. LS3 is the descendant of Big Dog, and Big Dog was a breakthrough in legged robots. Until Big Dog, most legged robots were either upright humanoids with 2 legs or sprawling 6-legged insectoids. With 4 legs, Big Dog is more stable than a humanoid and able to carry heavier loads. With an upright mammalian posture, Big Dog has better clearance than an insect body form. The problem with using a dog or any mammal for a robot design is that they are unstable. You can't stand up passively, fall asleep, standing up, and you fall down. To solve this problem, engineers led by Martin Buehler had to create a robot with dynamic stability. You can see how dynamic stability works because Big Dog is almost always moving its legs, even if it's standing still. It's sort of ironic, isn't it? But that's the trick. If you are always moving, then you are actively keeping your center of mass balanced between your legs. Now, dynamic stability is costly in 2 ways. First, it takes energy to always be moving your legs. And second, it takes a lot of sensing to do that balancing act. 50 sensors are needed to track the acceleration and tilt of the body, the position and force on the joints, and the velocity and attitude of the body. In many ways, Big Dog and LS3 epitomize bio-inspired design in robotics. Working from the anatomy and physiology of trotting mammals, engineers worked backwards from nature, identified the key functional principles, and then built machines that worked in the same way. The design of a robot's body then depends on its task and its workplace in which it is conducting that task. For novel tasks, roboticists often look to nature for ideas, as they did with Big Dog. When we think about inspiration from nature, there are some very surprising robots that have been built based on those principles. The streamlining that we see in dolphins and porpoises has affected a whole range of torpedo-shaped things, not only torpedoes in the water, but, for example, long-range ballistic missiles. The first long-range ballistic missile was the V-2 rocket. The V-2 was created by the Germans in World War II and was used against the Allies, most notably the civilian population in southeast England. Just like Whitehead's torpedo, the V-2 is a robot in the sense that it operates on the principle of sensor-guided movements. The German engineers built an automated controller for guidance based on a gyroscope and a pendulum. The Mueller Pendulous Integrating Accelerometer, or PIGA, thankfully, for short. Gyroscopes, what useful sensors they end up being. Now recall that we first encountered gyroscopes as the main component of the autopilot created by Elmer Sperry when he was building that aerial torpedo out of an airplane. The difference between Sperry's airplane and the V-2 is the required speed and accuracy of the gyroscopic response. Because the V-2 was traveling at speeds faster than sound, it needed to react quickly and accurately. A PIGA takes advantage of the fact that the torque from a spinning gyroscope can counterbalance torques that attempt to rotate the gyroscope in a different direction. In the PIGA, the pendulum would tilt its top arm to the right if the gyroscope weren't spinning. In flight, this PIGA is mounted so that neither the axis of the pendulum nor the axis of the gyroscope are aligned in the direction of motion. So as the V-2 rocket accelerates forward, the pendulum tips downward, causing the electrical contacts to close a sensor switch. That switch turns on the torque motor up on top, which then rotates the whole system until the gyroscope's precession is able to switch the torque motor off. Now, what the PIGA senses is both the magnitude of the acceleration and the speed of the V-2 rocket in that direction. If you know your acceleration and your speed and how long you are moving at that speed, your angle of takeoff also, then you can calculate where you're going to land using the simple physics of thrown balls and other objects called ballistics. You can go ballistic. Hence, a ballistic missile throws itself to hit a target. From a range of 100 miles or more, the V-2 could hit within 600 meters of its target. That's a measure of its functional accuracy. After World War II, the US and Soviet Union captured as much of this V-2 technology as they could. The V-2 jump-started our own ballistic missile programs and space programs. The first rocket launch from Cape Canaveral, Florida took place in 1950. For its inertial guidance, America's modified V-2 rocket, called a Bumper 8, carried a set of PIGAs that had improved accuracy. The basic design of the PIGA sensors worked so well, in fact, that many of the most famous rockets carried them, including the Saturn rockets that took humans to the moon. Because of their accuracy, PIGA sensors allowed the V-2 rocket to be independent of human control once the rocket was launched. Simple mission, simple environment, and independence from humans thanks to an accurate controller. Fully autonomous robotic systems have also been developed for defensive actions as well as offensive ones. And let me introduce you to a very important unmanned system used by the Navy since 1980. The Phalanx Mark 15, a close-in weapons system. The task of Phalanx is more complex than that of a V-2. It's not just to launch and land an explosive device. Phalanx has to detect, evaluate, track, and then engage targets that are rapidly moving and attempting to destroy the Phalanx's ship. The task of the Phalanx is to be the last line of defense against anti-ship missiles and high-speed aircraft. This is a do-or-die situation in which both speed and accuracy are critical. The environment of Phalanx is likewise much more complex than that of a V-2. It's not just the air, but objects in the air and objects on the water. And keep in mind that there are other ships in your own fleet here too, so the environment is mixed with friends and foes, sometimes intermingled. Now, what about human independence? In battle stations, the operator normally places the Phalanx in its autonomous mode, so it is actively using its radar to detect incoming targets. Because the Phalanx is built as a last line of defense, it has very little time to react. For example, it detects targets at a range of 3 nautical miles, can acquire those targets at 2.3 miles, and engages those targets at 1 nautical mile. If the target is a cruise missile, a human operator wouldn't even have time to hit the on switch. Because of the need for speed, the Phalanx needs a high degree of autonomy from humans. Under most battle conditions, the job of the human operator is to hit a hold fire button, if so ordered by the fire control command. The primary sensor systems of Phalanx are 2 radars. It has a wide view detection radar, a narrow scope radar also that focuses on the target once it has been acquired. Before Phalanx engages a target, it has to answer these questions. Is the target approaching the ship? And if the target is not directly approaching the ship, can it maneuver to hit the ship? If it is approaching the ship or can maneuver to hit the ship, is the target's velocity within the range that phalanx can operate? These questions are answered by calculating the heading and the course of the target over time. Knowing the heading and speed of the ship, too, the computer controller of the phalanx can calculate if the two paths will intersect at the same time. Changes in heading of the target indicate its ability to maneuver. Finally, changes in position over time indicate the target velocity. Once phalanx fires on a target, it uses its focused radar to track its own projectiles relative to the target. And using good old negative feedback control, phalanx then makes adjustments to narrow the distance between the actual and desired trajectory of its projectiles as it continues to fire. Phalanx can make these adjustments much more quickly and accurately than a human operator can. Even though Phalanx is automatically detecting, tracking, and engaging its targets, it's worth noting that it is not deciding who is friend and who is foe. All detected targets approaching the ship are treated as foe. This is one way around the difficult problem of combat identification, trying to categorize your targets. Now, admittedly, this is a very dangerous way to program a robot. You can't have your Phalanx system on automatic when your vessel is getting supplies delivered or the crew is coming back from shore leave. Now, with the success of robots like the Predator and the Reaper, the defense agencies of over 50 countries have active military robotics programs. The race is on to build new kinds of robots for war. So what's going to happen? Well, based on what's available in robotics and missing from military robotics, my guess is that we'll see the following technological advances. First, I expect to see more operational autonomy, particularly as sensor systems get better at identifying friends and foes. Second, autonomous robots will need to be able to adjust rapidly to changing conditions on the battlefield. So I expect to see machine learning in robots sent out on unmanned missions. Third, because robots can be made of any size, I expect to see many more robots that are small, and small robots to operate in swarms. One great advantage of swarms is that they can tolerate heavy losses and still carry out their mission. Now, those are my guesses, but what is certain, as Cayley's observations about birds and dolphins in vision, and Whitehead's experiments with unmanned torpedoes proved, is that robots will play an ever greater role in how humans wage war and defend themselves in the 21st century.